Okay. So, in the last class we did the Barabasi model. So, what did we learn from Barabasi model? That if rich gets richer, then what happens? The degree distribution becomes power law, okay. Something like this. Okay. So, that was clear. The initial model showed that you can have a exponent of -3, and then we went on to generalize this. Okay. So, what was the technique used? What was the technique used? It was a discrete rate equation, or master equation, whatever. But the basic concept was discrete time. So, we were thinking there is a time pk, then next step pk plus 1, pk plus 2, pk plus 3. So, time was discrete. Okay. So, what is the other way of thinking? Since graph is infinite, the basic assumption is, or the basic what have we seen, that these graphs are increasing or ever growing graphs. Internet is ever growing, okay. A power grid is ever growing, a peer to peer network is ever growing. So, the graphs are ever growing, but the degree distribution has an asymptotic behavior. This is the idea, that graph, it is not that the graph stops at any point, even when we are analyzing, the graph is not stopping. Okay. So, graph is ever growing, or what we can say, it is infinite. Okay. So, if graph is infinite, then if you consider a single event, what is a single event? A node coming, a node entering. So, a single event then is very, it is a very small event compared to the entire graph. Okay. So, then you can think this as a continuous event, hence the addition can be thought as a continuous event, okay, because each single addition is a very small, it is a small event taking just delta t time. So, the entire graph is basically addition of all these delta t's. So, we can think the entire event as a continuous event. And then if we think it as a continuous event, then what immediately we can do? We can use what? We can use some sort of integration and differentiation. Okay. So, this is an important tool which perhaps can be used. Okay. So, now let us think in terms of a single graph, single node k I. Okay. So, a single node k I, how many more edges are getting added to this single node at each time step? I am keeping the time step concept as previous. At each time step t, how many new edges join? Tell me. No, m nodes, a node comes with m edges, but I have a node with k I edges. So, how many new edges join that k I edged node? It is preferential attachment, we know. So, it is Ki by summation Kj into M, because there are M nodes. See, is this okay?
That
Okay.
is basically PKI.
No, I am taking a Ki, just a single node Ki. Okay, I am not taking all nodes with degree K. Okay, so what is summation K, Kj? This is delta K. Huh. What is summation Kj? Huh? So 2 into n into m into m. So this is Ki by 2n. And what is n? Number of nodes, and at each time one node joins. So what is n? T. So it is Ki by 2t. Okay, it is Ki by 2t. And what is Ki by 2t then? The rate of change of degree of a node with degree Ki. Clear? I hope this is clear. Okay, so then take this. Let us write this. dki dt is equal to Ki by 2. Then del Ki is equal to, we can integrate. What would this give? Log Ki is equal to log T half plus C. We can have log C. Okay. So when T is equal to Ti, when T is equal to Ti, then what is Ki? Nisha, what will be Ki? Moina? What is Ti? What is Ti?
Time at which the node Ki, time at which the node Ki is added.
The time at which node Ki enters. The time at which node Ki enters. Okay. So then what will be Ki?
Sir, Ki is the number of edges.
Yeah.
The time at which a node with Ki edges enters.
Yeah. So
But
what
we
is
have
Ki?
assumed that it is constant. M. No.
So what will be Ki?
M.
M. Good. Very good. Okay. So Ki is equal to M. When it is entering with M edges. So at that point Ki is equal to M. Okay. So our basic assumption is what? That everybody joins with M edges. So at Ti time, Ki is equal to M. Okay. So then let us put log. So if I put, then we get C, huh? So Ki, so now you get with this, just you can put and you can get the value of C. this has given you what? Ki is equal to t to the power half by c. Okay, and when t is equal to ti, then ti half m by c. So c is equal to ti half by m. Okay, so put this and you will get this. Okay, so I think you understand that immediately this step comes. I have put the value of c here, so ti stays here and m stays. Okay. Okay. So this is the first result. So we know Ki t. Okay. So if we know Ki t, now I want to ask this question, that I want to know P Ki t less than K. Okay. Why I want to know this? What is my objective? This is not my objective. What is my objective? What do I want to find? What do I want to find? Pk. Very good. So we are trying to find. This is the final objective. All of you agree? So let us see. Pk is now not a, it's a PDF. Here it is a probability density function. It's a continuous domain. So it's a probability density function. So if I think, say, this is say Pk and this is, or I can say this is Pk and this is Pk plus delta t. Okay. So what happens? Just tell me, if I have a PDF, this, what is this? What is this entire part? Pk. Okay, I should write it different. So this is K1, this is K2, where K1 is equal to K2 plus delta. Okay. So what is happening is P K less than K1 minus P K less than K2 is equal to actually P K into delta K. This area is, you get like this. I hope you agree with me. This total area minus this area is this small area, and which you get by the. So what is essentially happening is Pk is basically del Pk greater than something like del. Okay. Means I would write it in a more agreed. Okay. So now what is my objective? Basic objective is to find this, or find the functional form of this, then I can do the differentiation. Okay. Am I with you?
So in the first line, should it not be Pk integral of over k. It's
No.
you have written simply pk. That is
Yeah, this is cumulative. Pk was I maybe I have tried to say that this entire region minus this region is what you get as this small region, and this small region can be then approximated by pk2 into delta t. Okay. These are, maybe I should give a capital so that you understand that it is the entire area I am trying to tell. Okay? Okay? Okay, very good. So, now let us come back. What we want to find out? We want to find out T ki T less than k. Okay. So, what do we know? Ki T equals to, what is ki T equals to? M T by Ti to the power 0.5. Am I correct? Okay. So, now if I write, this is, I write ki T less than k, that means I can write M T by Ti 0.5 is less than k. Okay, no problem. So, then you can write, just with a little manipulation, Ti is greater than m square T by k square. Okay. So, what you can write, this is equivalent to P Ti greater than m square T by k square. So, Ti basically says time, or it says the nth node. Okay, we can think that always T is time and node. So, it is the Tith node which has entered. Okay, Tith node which has entered. Okay. So, let me write this once more. P okay. This can then be written as 1 minus Ti less than m square T by k square. Okay. Okay. Now, in the typical Barabasi model, what happens? Initially, you have some nodes. How many nodes do you have initially? When you start the process, how many nodes do you have? No. Barabasi model cannot start with 0 nodes. Huh? We start with m nodes. We can start with a m node which is a click, or m plus node which is a click. That is the initial bootstrapping of Barabasi model, that you start with m plus node which is a click. Okay. So, typically you can say that there are m0 nodes. Okay. Initially there are m0 nodes. Okay. So, at time t, how many nodes are there? Then huh? m0 plus t. So, I write t plus m0. Okay. So what is the probability that that tith node will be less than this? So the entire node is t plus m0. Okay, and this point is say m square t k square. So Ti can be this side or Ti can be this side. Okay, what is the probability that Ti will be this side?
M square T by K square by T.
M square, simple. I go do k square. Agreed? So this becomes 1 minus m square t k square t plus m0. Okay. Agreed, Shresh? It's okay. See, this is the entire time is t plus m square, and I am trying to see whether Ti is in this side or this side. So I just took a linearization. So if forget, if this is x, then this is, and this is y. This part is x by y, and this part is 1 minus x by y. What? No. Y minus x by y. Yeah. So exactly that linearization I have done. Okay. So are you agreeing with this result? Or if I go more fundamentally, it is ki t less than k equal to 1 minus m square k square. If t is sufficiently large, then what happens? It cancels. T is if t is greater than m0, then this becomes 1 minus m square by k square. Agreed? Okay. So we have this result. Now what we want to do? dpki. Huh? Because t is sufficiently large, I have just removed it. Okay. So this gives me 1 minus m square k square. Now what do I want to do? I want to differentiate this by k. This should give me pk. This I know. So if I differentiate this by k, what happens? This becomes 0 and this becomes m square by k cube. I think 2 m square by k cube. So now you come back, see, to the original Barabasi model. Okay. So the same thing, exactly the same thing, but in a different way. Okay. So what happened? First, okay, I will tell you the steps once more. What happened? We took initially a single node, tried to see its movement, and accordingly told about ki. Okay. And once I know ki, then I wanted to find out the cumulative distribution, that ki less than k. And if I know ki less than k, if I differentiate, I get pk. So these are the 3 steps which need to be followed to find pk. Okay. Okay. So, again this immediately points to one more problem. What is the problem? That y3. So, what needs to be changed in the model so that it becomes more flexible and not 3. In the previous case, what did we do? In the previous case, what did we do? In the previous case, instead of k summation k, we told no, it is k plus delta summation of k plus delta, something like this. Okay. That was our proposition previous. And what is this? What is this? Yeah, this is a randomness factor. Okay. This is what we called as randomness factor. Okay. This is what we called as randomness factor. Okay. Here we will try to see it is in a different way. Okay. We will try to play with this -3 in a different way. Okay. So, let us think that what is normal Barabasi model doing? Normal Barabasi model is just one node coming and getting added. Okay. But in a network formation, these are not the only events, there are other events happening. What are the other events which happens? Tell me. One is growth. Okay, growth we have accepted. Okay, growth is happening. What are the other events which can happen? Shomik, tell me one more event.
Removal.
Yes.
Removal of node.
It can be removal, very good. So, let us think that it is a growing network and I do not consider removal.
Rewiring.
Rewiring, very good. So, rewiring and what else? What else can it be? Tell me. Edge addition. Okay. Edge can be added, not node, but edge addition. Like you have a web page, you now add some more hyperlinks. So, you have edge addition. Okay. Okay. Very good. So, now let us see this three things combined together and what happens. Okay. So, I first talk about edge addition. Okay. So, it is addition of m new links with say prop p. Okay. So what happens is that what can happen, that you randomly choose a node. Okay, you randomly choose a node and then you attach the links preferentially. So, let us write two things: randomly choose a node and to attach preferential. Okay. Okay. So I keep this as a typical price model, because I can attach also to nodes which are not connected. Okay. That was the price model concept. That is why we give a 1. Okay. You remember that in price model, what was price model? Things are directed. So, what happens if I do not have any citation, I cannot get cited. So, that is why for bootstrapping we added this plus 1, if you remember. Okay. So, this is now can we write the rate equation for this? Let us try to write the rate equation for this. Okay. So, what is the rate equation? So, a k degree nodes, what is the change? This is what we have to write. So, what are the changes? That it can be either this end or that end. Okay. And if this end, if it is this end, then
Equal probability.
it is equal probability, and if it is that end, then it is preferential. So, you can write P m 1 by n, okay, plus P m summation k I plus 1 is k I plus 1 summation k I plus 1. Okay. See, it is actually 2 m edges are added, means m edges are added, but 2 m tips are there. If I add m edges, there are 2 m tips. So, that is why I have used m half. Okay. Okay. So, this rate equation is clear. Okay. So, now what happens with probability q? You can rewire. Okay. With probability q, you can rewire. What does rewire mean? You randomly remove one part. So, you have this, you randomly remove one tip of the edge, okay, and attach it preferentially. You have a edge, okay, you randomly pick one side of the edge, okay, and then what?
Change one of the inputs.
Change one of the inputs. So, randomly delete, attach preferentially. Okay. So, you are deleting randomly, attaching preferentially. Clear? I write this: delete rand, attach pref. Okay. So, now Bikash, tell me what will be the rate equation. Anybody? Nagarjun, can you tell me the rate equation?
You add the probability of deleting and probability of deleting and add randomly from the.
Yeah, so tell me what will be the rate equation. I try to write. See this, it will be almost similar to this.
Minus qm 1 by n.
Very good. Minus qm by n, because edge is deleted, so minus, and plus q m ki plus 1 summation of n. I should write kj for all j's. Okay. Very good. And what is the third event? Third event is growth. Third event is growth, and so what do I write? Tell me. Tell me, what should I write? It's the same, the previous thing, ki plus 1 summation of kj plus 1 into m, and now the third event will occur with probability 1 minus p minus q, because with p probability what is happening? With p probability what is happening, Pushkar? Edge addition. With q probability rewiring, and 1 minus p minus q is growth. Okay. Okay. So then now we can write the composite rate equation. Okay. So composite rate equation is basically addition of these three, and what do we get? dki dt is equal to p minus q m 1 by n plus m okay. Again n is equal to, what is n? Tell me. Yeah. Before I write n.
Number of nodes in the
Tell me, what is n? m0 plus hmm?
1 minus p minus q.
1 minus p minus q into t. Very good. Because only this many number of nodes are added. And what is summation kj? This time, this is the event when no edge is added. This is the event when no edge is added, if you remember. Now tell me. And at each other point, how many edges are added? M edges are added. And this m, each edge gets 2 degrees. Okay. So this again, so you can put dt and you can go on integrate. It's a little complicated integration, not very, just integration by substitution, if you remember. Okay. Arpit, you remember? Okay. So anyway, I think if you just use that e to the e concept, you can do the substitution integration. But let me just come to the final result. Okay. So it becomes complicated, but just see here there is no t, no t. Okay, it just depends upon PQM. Okay, these functions have no t, only t is here. So, it is in the same functional form as the previous one, but instead of 0.5 we have a BQM. Okay. So, okay. So, just see the previous thing, then you will remember. So, from there what we try to find out? We try to find out this PKT. You remember that you try to find out this PKIK, and accordingly you get t greater than something or t less than something. Okay. So, this is something which you get. Okay. So, our next objective from here is to find out PKI less than k, and from there you will again land up into having something that you land up into something more complicated. Okay. This is even not very important. The why I am putting this complicated thing is just to say that since this is not a simple equation. Okay, this is not a so simple equation. What we have to check? Like previously this was like m square by k square, something like this. Okay. So, m square by k square would always be necessarily positive and less than 1. It should be less than 1 because the largest value of m can be k. Okay. The largest value of m can be k. Okay. So, now tell me what is the condition which need to be satisfied? Yeah. So, this should be less than 1. Okay. If it is greater than 1, then this entire value becomes 0 and there is no meaning. Or what can be the other thing? This can be imaginary. So, it is undergoing complicated, it is basically a result of some complicated function, okay, and that function we do not know the value of that function, but that function can be imaginary also. So, we can have not well formed equation. Okay. We can have not well formed equation. Okay. So, then what happens if there is not well formed equation? Or c greater than 1, anyway greater than 1, all these conditions will not hold. Okay. So, only thing if this is between 0 and 1, then only PKIT less than k would function. Okay. So, this is the only condition when it will function, and if that happens, then we get again Pk is equal to will be proportional to k to the power gamma p q m, where gamma is equal to b p q m plus 1. Okay. So, in the end what we want to drive is that you do not have 3, but a important, it's varying, it's not 3, but it's varying. Okay. This is one point, and there is another very important point, which need to be said, that we have P and Q. Okay. You have P and Q. What is P and what is Q? P is the probability of addition of edge and Q is the probability of revarying. Okay. So, now it can be shown that if Q is greater than some Q max, okay, if Q is greater than some Q max, all this. So, there are many various variables, you understand, this is not a simple equation like the previous things, there are various variables. If Q is greater than Q max, then it can be shown that this power law scaling does not hold. The graph becomes more exponential. So, what does that mean? Can you tell me what does that mean? What does Q greater than Q max mean? That there are too much of revarying going on. So, as soon as too much of revarying starts, the graph's power law behavior begins to fade. So, after Q greater than Q max, exponential power law changes to exponential. So, there is a phase change. Okay. So, I would show you this picture, see this picture. Okay. So, what is happening is various P's. So, what you have to have, you can understand that P plus Q has to be less than 1. So, this is the condition, and now what is, so this is the only feasible region. Okay. And now what is happening, as Q is becoming more than a Q max, it is changing from scale free to exponential. So, the take home is, number 1 is that you can always change the exponent, and number 2 is that you can, if there is too much revarying going on, we have to shift, or the graph does not stay power law any further, it becomes exponential. So, actually what is the main problem of Barabasi model? The main problem of Barabasi model is, if I am a older node, then I will get higher degree. So, basic idea is, if I am a older node, I have higher degree, but if you see in a web page, say in a web page community, it is not that the oldest web page has the highest community, highest link. Okay. It's true again that early movers have higher links, but it's not linearly true that if I am early enough, then I will get the highest link. But in Barabasi model, what we see, it's 1:1. It's the relationship holds that older nodes have higher links. So, in order to circumvent this problem, so what can be done to the model? Why? So, let us ask this simple question: why do younger nodes or younger pages say get higher link? If I ask this simple question, why do younger pages get higher link? Why? Yeah. So, the point is that maybe this page is good. Okay, good in many, it can be in many sense. Okay, it's more relevant, it has more recent information. So what happens in the model? So, can you tell me what's the importance of this in the model? The importance is, it's not only link property, there is a node property also. So, still now what we are seeing? If higher link, touch connected with it, but we are not seeing the quality of the page. Okay. If the person is highly connected, connect to this person. We are not seeing what is the quality of that person. But in a web page, it's not only it's true that people get information about higher linked things, but also people see the quality of the page in order to get it connected. Okay. So, then what happens in the model? You will have Ni, okay, or it is a neta I, okay, which is node property. Okay, neta I is node property, and what we can think that it is chosen from a degree distribution, or from a distribution, sorry, not a degree distribution, but from a distribution rho neta. Okay. And what will be the attachment probability now? It will be a joint distribution of the weights and the degree. So, then what we can write it as okay. Clear? So, now what are the steps, can you remember? We have to first okay, and that we get, since we are attaching k links, we get it like this. Okay. And from that, what do we do? So, I hope you are understanding that there are m links, okay, and it is going by this joint distribution, that what is the weight of k I, what is the degree of k I, summation by the constant factors. Okay. So, once this is there, then you can calculate, what do we calculate? We can calculate k I t, or we can calculate k is given a particular weight. I go by your weight, okay, and that we see is okay. And what is beta Ni in Paravasi? What is the exponent value in the Paravasi model? 0.5. It is 0.5. Okay. Okay. So, again this point which we were thinking that why should it be 0.5, it can be anything, so that we do not land up into k to the power minus 3 is answered, that if you give node weight, then it does not remain 0.5. Okay. And so, what will be the value of beta Ni? It should be between something between 0 and 1, okay, because it cannot grow faster than t. Okay. So, and what we find is beta n eta is equal to n by c, and if we it will depend. So, this exponent p k will depend upon the distribution rho n. If rho n is like this, okay, rho n is the distribution of the weights, we again see that p k becomes proportional to k to the power minus 3, and we get a power law. Okay. And if we take an uniform distribution where neta I varies between 0 and 1, we get p k proportional to k to the power 1 plus c star log k. Okay. And for some cases, it is not true that p k always stays power law. For some cases also we can show that p k becomes exponential. Okay. This is same as the previous test case where we saw that q max, if q max becomes more than something. So, if there is some role of weight, if weight is arbitrarily distributed, it need not stay power law, it becomes exponential. So, neta I is uniform means I am taking up any value from 0 to 1. Okay. The distribution of rho is uniform. So, the probability of choosing 1 and probability of choosing 0, everything is same. Okay. And then for some cases we also get exponential distribution. So, this is how weight based things, if I allow weight, it varies. So, next class what we will do, we are now ready with the continuum model, we will use it for superlinear and sublinear attachment. Okay. Thank you.